right, cool. We're live. All right, thanks a lot for attending to this talk. This is a sort of, we're going to start very generic and then we're going to go down into Moonbeam. But the idea here is it's a little bit of a discussion, right? It's not going to be a workshop, even though it was supposed to be a workshop. But I feel that, like coding live, it's not really a thing. And so I prefer just to create an interesting discussion with the audience at the end for questions. So my name is Alberto Viera. I do developer relations at Moonbeam. And today we're going to talk about Crosschain EVM calls in a multi-chain future, right? If we think about, I guess the first question that we get asked is like, why Crosschain EVM calls are important, right? That's sort of like super important to address this question first. And so basically, if you think about the history of blockchain, right? So here what we have is time, and then on the y-axis, there's no y-axis, but it's like the number of blockchains. If you think about the history of blockchains, it was really hard to build blockchains back then, right? You had Bitcoin, then Litecoin, and then Dogecoin, and then Ethereum and so on. But right now, if you think about where we stand today, there are over 120 blockchains out there existing, producing blocks, decentralized, and so on, right? And so there was a shift in sort of like the way people were thinking of like interacting with the centralized technologies. Back then, like I said, it was really hard to create blockchains. And right now, thanks to things like the the Cosmos SDK, Substrate, which is like the Polkadot SDK, and then the OP stack, you can create a blockchain in minutes. And so, you don't have to think about, oh crap, I have to program my runtime, I need to program the client side of things, I need to program the peer-to-peer network. Everything is sort of given to you as modules, packages, whatever you like to call them. And then you got to work on ensuring that your logic is contained within modules and things and code. And so back then you had few blockchains, and nowadays, there are many, many names now out there. It's difficult to keep track, to be honest. And so it is kind of clear that the future is both multi-chain and cross-chain. And actually, I had a conversation with a guy in ETH Barcelona. I was calling the future multi-chain, but it's like, hey, buddy, like Vitalik says that multi-chain is like multiple chains within one consensus that don't necessarily understand that there are other chains with other consensus. So that's why I added the cross-chain bit. So it's both multi-chain and cross-chain at the same time. So when a project says they're multi-chain nowadays, right? We have an example of Uniswap where they say they're multi-chain. What they actually mean is that they're either two types of multi-chain approaches, basically, okay? The first one is it's what we call centralized deployments, in which you have sort of like, okay, I have my deployment in XYZ blockchain, but I am connected to all these different blockchains. And if you want to use my protocol, I'm asking you guys to actually bridge over funds to my protocol and interact with my protocol in the blockchain that I've decided to deploy, okay? And this is not great because you have the bridging user experience and security risk, and you're also addressing a limited market. The limited market being is that the users that are willing to assess the risk of bridging and going through the user experience, okay? The other type of deployments is what we call multi-instance deployments. And this is where actually I should have mentioned Sushi, right? So it means, oh yeah, we are multi-chain, meaning that we have the same set of smart contracts deployed everywhere. And so you're actually fragmenting users, features, and liquidity, right? So we know the typical Uniswap v2 style DEX, it's more efficient the more liquidity it has. But if you have multiple mini Uniswap v2 deployments everywhere, you're just, you're not being as efficient as you could. You're fragmenting users, right? You have the SushiSwap community now being fragmented among 10, 12, 13, 15, 20 different blockchains. And then you're fragmenting what I like to call experiences. It's terrible when you're like going to adapt and then you have a drop down of blockchains that this multi-chain deployment is actually, it's able to be in these blockchains, and then you have 20 to select from. And like, what is that, right? For me, if you think about the multi-chain and cross-chain future, it should be that people are interacting with blockchains without even them knowing that they're doing it, right? I was at ETH Bogota last year, and in the hackathon, there was a project called No Chain, or actually in Spanish, No Cadena. And there were a wallet that wanted to sort of abstract the idea of blockchains. Like you would have 100 USDC, 100 USDT, without telling you that they were like in 10 different blockchains, right? And if you saw an investment strategy, let's say in XYZ blockchain, they would internally do cross-chain calls to ensure that your funds will move to this one blockchain and use that investment strategy or whatever it is. And that for me is sort of like, in my head, the multi-chain cross-chain future that we should be targeting, right? Because we're not going to onboard, the next 100 million users or whatever with 20 different blockchains, telling them to move funds around. That is not a great user experience. And so with that, we introduced the idea of something called connected contracts. It's just a fancy name, marketing name. It's nothing specific or bounded to Moonbeam. Chainlink actually started talking about the same idea when they launched CCIP like this week or something, but they started talking about the similar concept. And the idea of connected contracts is that you should be able to reach any user, any asset, or any service from whatever blockchain you're interacting with without understanding all the complexities that are happening behind, okay? So a great example of this is a project called Prime Protocol on Moonbeam, which is still not ideal for this like gold of end user that you try to target, right? But Prime Protocol it's a protocol that is deployed to multiple blockchains, and it has sort of like a hub and spoke model. All the hub contracts are deployed on Moonbeam, but then the spoke contracts are deployed everywhere. What this allows is that, for example, a user that wants to mint a stable coin on Ethereum, but they have their collateral in, let's say, Avalanche, they can lock their collateral in Avalanche, and then the protocol would say, okay, basically via cross-chain protocols, okay, so this guy has the collateral on Avalanche, so I can actually mint the stable coin that it's backed by collateralized basically by these assets in Avalanche. And the user then can have this like liquidity, this new liquidity in Ethereum without even knowing that they use Moonbeam, knowing that they send a bunch of cross-chain messages. They're just worried about, the Prime is just worried about the user experience, that the user is actually engaging on. And so, the key innovation that allows what I was just mentioning, connected contracts, to happen, it's called general message passing, okay? There are many terms for this. I like general message passing. There's arbitrary message passing, cross-chain bridging, whatever you want to call it. General message passing is what allows two blockchains to be aware of the other ecosystems, right? If you think about Ethereum, Ethereum has no clue that Moonbeam exists or that Avalanche exists or Polygon. They're a self-sovereign chain with their own consensus. Their consensus only cares about the state transitions that are happening within Ethereum. They don't care about what's happening on Avalanche at all. They don't even know. Like a contract on Ethereum literally doesn't know that a contract on Avalanche exists, right? And so general message passing allows these sort of like two blockchains ecosystem to communicate with each other and exchange messages. There are many ways to do this, okay? But we'll get to that a little bit later. And so basically what this allows is that blockchain one can say, oh crap, I mean, there's a multiple worlds of, or like applications built on blockchain one are now aware that there's a million users out there on different ecosystems, different assets, different services they can access, right? So think about, for example, I don't know, I have a prediction market running on Moonbeam, but then I'm a project on Ethereum, and maybe the prediction market team on Moonbeam is great, and I want to access that prediction market service. They could do it now with general message passing, right? So this creates sort of like an interaction between these two blockchains that can now communicate with each other and then exchange services or whatever they want to do. And so now let's talk about consensus and cross-chain. And so I'm first going to sort of like generalize the idea of cross-chain, and then we're going to go through different sort of means of cross-chain, right? So I mean, this few slides are very generalized, and then don't judge me on that. But then we'll sort of get more into it. So once again, we have blockchain one, blockchain two, and two different self-sovereign chains that have their own consensus mechanisms, right? The sort of like premise here is that these consensus are robust, right? I mean, they can prove with enough BFT that the state transitions that are happening are okay. And so basically, general message passing, what it does at its core is connect isolated consensus systems, like I mentioned before. But the way that they normally do this is that there's a cross-chain message on blockchain one. This cross-chain message, all it is a contract that states via an event saying, hey, user A wants to submit this transaction with this data on chain XYZ, okay? And it's just gonna emit an event. That it's still, if you think about it, that it's still contained in the consensus of one. that is not actually communicating, the consensus one is not communicating that to another consensus, that it's something that is happening on consensus one. But then what you add, it's an intermediate consensus or a GMP protocol that it's in the middle, that it's able to fetch that event and understand it and say, okay, someone on chain A or blockchain 1 wants to execute this call on blockchain 2. And so basically now you have an intermediate consensus layer that it's able to sort of understand this sort of ask and then execute it on blockchain 2. But then, I mean, look at this picture, right? I mean, now you have 3 different consensus mechanisms working together for one cross-chain message to move, right? And this is one of the sort of the major sort of deal breakers for a lot of projects when they want to do cross-chain execution, is that now you don't have one consensus mechanism of a self-sovereign chain, you have 3 consensus mechanisms working together to execute a cross-chain action. And so I think that, in my opinion, you know, a lot of the things that are happening right now with bridging and GMPs, it's due to the fact that it's sort of like early stages in how mature this technology is. I mean, I'm talking to you here, and then like last week, it was all the multi-chain drama, right, and things like that. We've heard about hacks with Wormhole, with other bridging protocols that have happened. And so in my opinion, it's mainly because this technology is quite immature right now, and we need it to be mature enough so that cross-chain actions can now rely under this intermediate consensus without any issues. I also like compare this to Ethereum in 2017 when we had hacks at a smart contract level that, you know, they were happening quite a lot, and because right now these hacks are not really possible because we've learned so much of like how to prevent. They still happen. I'm not saying they're not happening, right? But you know, it's just sort of like as the technology matures, these things will happen less and less often. And so one thing that is happening here, if you think about it, is that there's a verification step that it's being done, right? In this case, the verification step is done by the GMP protocol at the middle, which has its own consensus. Like I said, this is not always true, but there's a verification of the message that happened on consensus 1 so that it can be executed on consensus 2. And so generally speaking, once again, it's really hard to speak about all the different possibilities because, you know, we only have 50 minutes. But generally speaking, there are 2 main ways of verifying verification mechanisms between 2 blockchains that are talking with each other. The first one, and probably the most difficult to understand, it's the native verification. So this is not the example that I showed you before. This is a different type of verification mechanism. And this is the one that it's mainly used by Cosmos and IBC. The way that this works, once again, the premise is that you have 2 separate blockchains that have 2 separate consensus mechanisms. They are self-sovereign and they don't trust each other, right, which is the premise of blockchain usually. And then what happens is that there is a layer where there are cross-chain messages moving. Okay, this could be relayers. They could be that, you know, blockchain validators in blockchain 1 are aware of validators on blockchain 2 are aware of like messages that are being sent by blockchain 1. There's a way for messages to move from blockchain 1 to blockchain 2. We're just generalizing it like that, right? But there's another layer on top of that, which is called light clients. This is one example of native verification. It's not the only one, it's the one that is mostly used, which is with light clients, right? And light clients, what they do is that blockchain 2, it's running some sort of client that it's the only thing that this client is doing is providing the minimal things that it needs to check that the message was sent on blockchain 1. So it's not running the entire consensus, the entire network, the entire state. It's just running a thing that it's as light as possible, light client, of blockchain 1 to ensure that the thing that happened on blockchain 1 actually happened and was finalized, okay? Like I said, this is how Cosmos usually works with IBC. When you have 2 blockchains in Cosmos that are doing IBC cross-chain, they're running light clients of each other, checking everything that happened. I'm not an expert, by the way, in Cosmos or anything, so I might be saying some things that are not right, but I think generally this is how it works. This is a problem, though, if you think about it. This is not really scalable, right? If we're talking that there's going to be, I don't know if I mentioned it, but there's like over 120 blockchains, right? I mean, if you're thinking about one blockchain communicate with 10 others, it means that they have to run light clients of 10 other blockchains. But now scale is to 100, to 200. It's really hard to scale these technologies like that. The other type of external verification is what I actually showed you before. Basically, you have an intermediate. Notice that in this case, you don't have an intermediate consensus, right? Why is that? Because blockchain 2, it's kind of running the consensus of blockchain 1, okay? And so in this case, now you have an intermediate consensus that acts as a relayer, but also a verification layer of the things that are happening on blockchain 1. Okay, so in this case, now you're trusting this middleman, this party. And that's how a lot of these like bridging protocols work nowadays. This is way more common than native verification. Why is that? Because this is really more scalable as well, if you think about it. All that needs to happen is that this GMP protocol needs to be able to support all the different blockchains, right? And that's why you have, for example, protocols like Wormhole and XLR and Layer 0 and whatever, like they're supporting many, many different chains, right? Because they can adapt their tech, their client in the middle to sort of support all the different protocols. So cool. Hopefully this is a little bit clear. Actually, optimistic bridges, which is also very famous, especially in L2s nowadays, they actually use external verification as well. It's a little bit different because in optimistic bridging, you're just like submitting a transaction and hoping, you're saying optimistically, I am actually telling the truth. And if someone proves that I'm not telling the truth, it will escalate and you might get slashed depending on how it works. But you're relying on an external mechanism to say if something is valid or not. Cool. So let's go through some examples of like cross-chain protocols. So we're going to talk about 3 because, like I said, there's like a gazillion, so it's really hard to to discuss them all. A lot of them are actually variations of one or the other. They're also like CK ones, but at the end of the day, they're either native, normally external, or native verification mechanisms. So the first one we're going to talk about is XLR. So XLR, basically they connect, they're a Cosmos SDK-based chain, proof of stake. They have their own consensus mechanism, like I said, based on proof of stake, in which I think they implement slashing if any of the validators does something malicious. That might not be true, but maybe I think it is actually. And so what happens is that apps and users on any of the blockchains that XLR support, they can interact with the gateway contracts, right? And the gateway contracts basically is like the middleman contracts or the intermediates between the apps and the users and the XLR protocol. So generally speaking, what happens is that you have some events that are emitted by the gateway contracts, and then the validators of the XLR blockchain, let's say, they pick up these events, they then discuss between themselves, they sit at a table and say, hey guys, is this valid or not, via MPC and other mechanisms. And so basically they approve the message, and then they get executed via relayers back to whatever blockchain that message was destined, and then through the gateway contract and to the end user or application, more or less, okay? What's important to understand, once again, is that this is normally what changes, right? The consensus mechanism of the middle is what normally changes in external verification protocols like XLR. XLR works a little bit different as well, in the sense that if you want to send, let's say, tokens from Ethereum to Moonbeam, they actually will provide an address that you need to deposit this funds to, right? So like I said, the nitty-gritty of each protocol is very, very unique to themselves, but the general idea is normally this, okay? Another very famous bridging protocol is called Layer 0. The way that I see Layer 0, it's like a mix of light client technology with like oracles and relayers. So it's not native verification, it's not fully external verification, it's a little bit of a mix, at least in my opinion. And so basically what happens here is that you have apps and users that are interacting with what is known as Layer 0 endpoints. It's like XLR gateway contracts, just a different terminology. And then these Layer 0 endpoints kind of emulate something they called marketing name ultralight nodes, okay? So the ultralight nodes, all they can do, it's verify that a state transition happened on an origin chain, but they need external information. They're not running like clients, they're not running the latest states hash and proofs and headers and everything of the other blockchain. They need the information to prove it, okay? So that is the main difference between ultralight nodes and light nodes, at least from what I understand, because this is like, you got to understand like there are like a million bridging protocols, so it's really hard to be a master in all of them. So how this works is basically the Layer 0 endpoints on the origin chain will, basically the user will submit the transaction that they want to send, and then the ultralight nodes or the endpoints will basically tell the oracles and the relayers. There are two components of security here, that they're separated. So instead of having one only consensus mechanism that is controlling everything, now you have like two separate consensus, right? You have things called oracles and things called relayers. And they cannot collude. If they collude, layer 0 security sort of like thesis gets broken, basically, okay? So ideally, right, if you use oracles as, for example, Chainlink as oracles, Chainlink should be robust enough so that they will not cheat, right? That's the whole premise. And then basically, the oracles will submit the block headers to the ultralight nodes on the destination chain. Remember that I said that ultralight nodes, all they can do is proof. It's validate the proof, right? And so basically, by the oracle submitting the headers and then the relayer submitting the transaction proof, they can actually say, okay, this transaction is valid, so I'm going to execute it on the destination chain. So this is a very quick summary of how layer 0 works. And basically, like I said, this is like a mix of native external and a mix of native and external verification, because it's using a little bit of the concept of light clients, but it's not really like light clients, like I was showing before. And then the cool thing about layer 0 is that you can choose as an application your own oracle and relayer. So you can actually run a POA. So, hey, I trust my own oracle and my own relayer that I'm running. I can do it. The problem is that, you know, if you set up your oracle and relayer and then for whatever reason they get compromised, you're screwed, basically. So it's sort of like you can choose which is good, but sometimes it's not good. It just depends on the security premises that you want. I'm recycling a lot of the images, as you can see. So this is now Wormhole. Wormhole is once again, generally speaking, similar to like external verification protocols in which you have now Wormhole contracts, absent users, Wormhole contracts, and all they do is talk to what they call the guardians, the Wormhole guardians, okay? So Wormhole guardians are kind of like a proof of authority consensus in which they have really, you know, validators that have really good reputation in the ecosystem, and so basically all they have to lose is sort of the reputation. And so basically I think they have 26 or 28 validators. And so basically now the validators will say, hey, this message is actually valid, but you know, they don't do anything else. They just say, hey, this message is valid and it's ready to be executed in whatever chain this message will be executed on. And so now what happens is that a relayer needs to grab that message, that it has like a VAA, what they call a VAA. It's like the proof that the message is valid. And they go to the Wormhole contracts on the destination chain, and then the VAA gets actually verified by the Wormhole contracts, and then you can execute the message, okay? Once again, this is a very clear indication of external verification because you have an external consensus that it's sort of like you're trusting that consensus to communicate your two blockchains, okay? So, if you want to learn more, to be honest, this document, it's really helpful to understand bridges, and they have, this is a Uniswap bridge assessment document that they released, I think, 2 months ago, maybe. In this document, they were sort of thinking about what cross-chain protocol they wanted to use for Uniswap deployments that exist out there. And this is their opinion. It's not that I share it or not. I just don't want to be put on the spot. But basically, Uniswap decided to go with Wormhole and with Axelar for their cross-chain deployments. They had really good comments on other bridges as well, and they will consider them as long as they make some changes and so on. But it's really good because they provide a really high detail. They provide a summary of how all the bridges work, or main bridges work, and then the details of like the downsides of some and then the upsides of some. And so it's a really cool document that is really well summarized. But this is, like I said, the opinion of the committee that worked on Uniswap on the bridge assessment side. So, before going to this side, I want you to remember the external verification slides, right? That you had 3 consensus mechanisms, and then now you had to trust that if any of these 3 consensus break, the whole cross-chain premise, basically, it's broken, okay? It gets broken. So let's talk about Polkadot's and Moonbeam's cross-chain calls. So I don't know if you've ever heard the song Polkadot's and Moonbeams. That's a Frank Sinatra song back in the day. That's where the Moonbeam name comes from. And so yeah, let's talk about cross-chain calls and how it works in the Polkadot ecosystem. Because if you don't know, Moonbeam, it's a blockchain inside the Polkadot ecosystem. And so, I mean, I think this image speaks by itself, but basically, in the XCM architecture of Polkadot, in the cross-chain architecture of Polkadot, right, parachains, which are blockchains in the Polkadot ecosystem, already trust Polkadot for security, all right? The parachains themselves or blockchains themselves, like Moonbeam, we don't have our own consensus. We cannot say that a transaction is finalized or is valid or not. We trust on Polkadot to give us that finality. right? And this is a big shift in how things normally work because when then parachain A or blockchain A wants to communicate with parachain B or blockchain B, they're already trusting the Polkadot consensus. So they don't really need to trust an external consensus to do cross-chain. And that's a big shift in how things work. Even in Cosmos, right? Cosmos, that's one of the biggest differences. When people ask me about the difference between Polkadot and Cosmos, this is the main difference that I normally tell. That this is called, in Polkadot, this is called the shared security. And Cosmos kind of understood that this is a deal breaker for a lot of people because in Polkadot, I can build my own blockchain to upload pictures of my cats if I want to do that because I'm a weird person and I just like to have my picture of my cats in blockchain. And from day zero, they'll be finalized by the blockchain, the Polkadot security, right? While on Cosmos, for example, I need to create an economic model that will allow me to secure my blockchain of my pictures of the cats, right? So that's not really that feasible. And so the whole premise of Polkadot is that these blockchains, these participants on the Polkadot ecosystem will get security from the Polkadot relay chain. And so when these parachains start exchanging XCM messages, you can clearly see the difference between this and the model that I was showing before, right? In this case, all the participants here are trusting on the same consensus. So basically, the state transitions that are going to happen on parachain A or blockchain A are going to be validated by the same consensus that it's going to validate the state transitions that are going to happen in parachain B, blockchain B. And so I really love this picture compared to the other one because it clearly shows that you only have one consensus basically checking everything. And so this is actually pretty cool for interoperability. And so with that introduction, let's talk about XCM. And XCM, if you're not familiar, this is like the language that Polkadot blockchains or parachains use to interoperate internally between them, right? So if you think about what we were discussing before on cross-chain calls between Axelar, Wormhole, and everything, normally the calls, what they have is basically you need to know the contract that you're targeting, if it's an EVM blockchain, and the data that you want to execute on that contract, right? That's normally what happens. Token bridging, all it does is it's basically wrap these calls into a token abstraction layer in which now the general message is going to be the same, but instead of just being that, you're going to just go to this contract and mint these tokens and give it to this user, right? And so in XCM, it's a little bit different because it's more generalized. It's a little bit of the outside of the EVM world. And so basically XCM, from a really practical and simplified perspective, it's a message with XCM instructions, okay? So if you want to do something, you just don't say one instruction and that's it. A combination of instructions will result in a concrete action happening in destination blockchain, okay? So it could be, think about it, it could be like, hey, Ethereum, I want to buy some of your execution time, some of your block space. I want you to grab this call, execute it on the smart contract, and whatever funds are left, just deposit it to this address. That is something you can do on XCM because there are instructions that if you combine them can actually do that sort of action. And so basically, if parachain A wants to communicate with parachain B, parachain A will execute some instructions on the origin chain, and then some instructions are going to be executed on the destination chain, and then, like I said, the combination will result in something. So if, for example, you want to do token transfers, you just grab a set of instructions, right? You just grab some instructions on Moonbeam, some instructions on the destination chain, execute them, and the end result is going to be a token transfer of, let's say, DOT from Polkadot to Moonbeam or something like that. You can also do remote execution, right? You can actually say, hey, from Polkadot, I want to call this EVM contract on Moonbeam and do X, Y, Z. So I actually have, for example, a demo in which someone on Polkadot can do a Uniswap v2 swap on Moonbeam, right? Without even having to sort of like go to Moonbeam, change the wallet. Okay, let me take my ledger out. Let me plug it in, change the wallet here from this network to this network, and then execute the call. That could happen remotely completely. I can just be in Polkadot, use my Polkadot wallet that I love. I don't have to jump ships or everything. You can do it from the origin chain, which is actually pretty powerful. And so in XCM, there's a concept called the sovereign account, which you can, if you know about token bridging, normally what happens is that you lock the tokens on one contract on one side, and then you mint the representation asset on the other side of the bridge, right? sovereign accounts, it's kind of similar to these smart contracts where you lock the tokens, but they're actually accounts. They're not contracts. They don't have code in it. And so basically in Polkadot, if you've never seen this image, this is a typical image of how Polkadot looks, right? You have the Polkadot relay chain or the Polkadot blockchain, which is securing a bunch of like ships that connect to it, and one of them is Moonbeam, basically. And so this means that, for example, Polkadot has an account on Moonbeam. It's a keyless account. It doesn't, I mean, it has a private key, but no one knows what it is. And basically, the only way to control it is via XCM actions, okay? So via XCM messages, via Crosschain messages. And the sovereign account basically is the message sender, the first message sender of a Crosschain call, okay? And then you can actually change it if you want. And so this is really cool because in XCM, you can do something that you cannot do with Crosschain EVM calls, right? And if you think about it, right, if I am on Ethereum and I'm doing a Crosschain call to Avalanche, the message sender on Avalanche is not going to be me. And it's not an account that I control. It's going to be someone in the bridge, the relayer or whatever it is. And that limits a lot of what you can do because you're going to create this experience that I was talking about in which you can stay in your own chain and remotely execute in some other chains, you know, with like a virtual account that you have, right? I think you can do something like that with account abstraction, but I've never seen like an implementation of this actually live or anything. So with XCM, you can do that. And the cool thing is that using some special fancy XCM instructions, you can actually say, okay, Alberto on Moonbeam has an account on Polkadot, and Alberto on Moonbeam has an account on whatever other blockchain. And this is the example that I was telling you before, that I can control, I can do whatever action I want on Polkadot, so I could do staking on Polkadot, but I can just do it from Moonbeam if an application would be built that you can do that, okay? So this is, once again, really powerful because this is completely decentralized and trustless, and you can create these cross-chain experiences that are way better than the typical bridging experience that we have today. And so this is sort of the premise of what I've been talking about right now with remote dispatchers, is that, you know, in Polkadot, you'll have an ecosystem of blockchains that will offer services, all right? So for example, there's a blockchain in Polkadot that can do automation. It means that, imagine you're in a DEX, right? Let's say SushiSwap or whatever, and you're doing farming, and then you want to claim your farm rewards, and then you want to re-put them in liquidity. You got to do how many clicks, you know, how often you got to do it. It's a terrible user experience. But on Moonbeam, using XCM and remote dispatchers, in your application, you could have a little button that says, automate this annoying action by clicking here and just signing a transaction. And what would happen is that Moonbeam will communicate to a blockchain that does automation, and then this blockchain will, like every so often, talk to Moonbeam and say, hey buddy, it is time to do this farming, and then you do this farming, and you put these assets back to this liquidity pool, et cetera, right? So the cool thing about Polkadot and the ecosystem that it's creating around this cross-chain experiences is that you'll have, you know, Moonbeam will be much more than just another EVM. It will be an EVM that will provide services via cross-chain integrations, and then all these other services can tap into Moonbeam's EVM for cross-chain calls. Yeah, so let's go a little bit into cross-chain EVM calls via XCM. So we talked about a little bit before about, you know, cross-chain calls, generally speaking, with bridges like Wormhole, Axelar, Layer 0. But let's now go through sort of like how this works on Moonbeam. And so first, let's sort of understand at a very high level how a regular EVM call works on Moonbeam, okay? So, and some of these things actually are applicable to other blockchains as well. So you're familiar with the term Ethereum compatibility, right? I mean, you have Ethereum, for sure, Ethereum is Ethereum compatible, but then you have Avalanche, you have Polygon, you have BSC, and they're all Ethereum compatible. What they mean with that is that they have an EVM, right? An EVM is a state transition machine that it's able to say, I have a state, I'm going to execute these transactions, and I'm going to calculate a new state. But you also have much more than that. I don't know here if you're familiar, but Hardhat, Ether.js, MetaMask, and all these tools, all they do is provide a nice interface for users and developers for the Ethereum JSON RPC, right? At the end of the day, Hardhat or Truffle or whatever, they're doing a gazillion of JSON RPC calls to a client, right? And the client is able to understand these RPC calls, and then it's executing an EVM call if it's doing an EVM call or whatever. And so when a chain says that it's Ethereum compatible, they have a lot more than just an EVM. They have an Ethereum-compatible client in the sense that when you connect MetaMask to Avalanche, MetaMask doesn't know that it's, I mean, it does know that it's Avalanche, but what they're actually doing is just sending a bunch of JSON RPC calls to this endpoint that is an Avalanche endpoint, and the Avalanche endpoint is able to understand the RPC calls and say, oh, okay, hey, this guy is asking me for this balance of this account. I'm going to return it. And then MetaMask is able to understand that and display it nicely to the user. And so this is, at a very high level, how this works on Moonbeam. It's exactly what I just described. So basically, you have apps and users that are interacting with what we call frontier RPC extension. So this is basically what receives the Ethereum JSON RPC calls. Okay, so let's do ETH get balance or ETH send raw transaction or whatever it is. And it's able to sort of like translate this into like Substrate or like Rust. The Substrate is a framework that Moonbeam is built on top of. So the Substrate terminologies or Substrate things, right? And then we have these modules that are part of Moonbeam that each do something very specific, right? So the first one is the Ethereum model, which is going to validate the transaction. It's going to ensure that the transaction is valid from like a signature perspective, whatever it is, and so that you know it's not failing because it doesn't have gas or whatever. And then it's going to sort of like send the valid transaction to the Rust EVM. So our EVM is based on the Sputnik, is it Sputnik or Open Rust EVM or whatever it is? And then you're accessing our EVM via a module called the Palette EVM or the EVM module, which is like the dispatcher to the EVM. And now the EVM is like I said, it's basically a state transition machine in which you provide some inputs and it's going to calculate the output, right? And that output is going to result at a high level in some Ethereum logs, right? And the Ethereum logs is what you actually see in the get transaction received or like an Ether scan that they just show it in a really nice interface and so on. But basically, this is really straightforward because you have a user signing a transaction with their private key that it's interacted with Frontier or whatever RPC client you're using, and then there's with some magic you get to the EVM and then there's some logs, okay? Now, when you're doing remote calls via the XEM, remote EVM calls via XEM, it's a little bit different because the signature happens in a completely different chain, right? It could be a completely different consensus mechanism. They could sign with only fruits or whatever. You don't really care how like their consensus mechanism is. But then when the XEM call arrives on Moonbeam, you got to be able to dispatch this call to execute it on the EVM, right? And so the way that this works is that there's a new module called Ethereum XEM module that it's going to check that transaction is valid before executing the EVM. One of the key differences here is that the signature happens on the origin chain, but when it reaches Moonbeam, the signature has no validity, basically. We cannot say how we interpret this signature because, like I said, it could not be using ECDSA. Maybe it's using SR25549, which is what Substrate uses, right? And so we have to forget, on Moonbeam, we got to forget, okay, the signature doesn't really care. How do we make this transaction valid? And this is via XEM instructions. So there is an XEM instruction, like I was showing you, that it's able to create a new account on Moonbeam that it's a keyless account. So we don't know the private key. If we don't know the private key, how do we sign this transaction? We don't really sign the transaction because we know that this account that we generated, we calculated, is coming from a signed account, a signed extrinsic or signed transfer on an origin chain. So the only way that we can calculate, and we know what origin chain is, in Polkadot, every chain knows what the other chain is, basically, by a chain ID, which is called the parachain ID. And so we can know, okay, this transaction right here was signed by Alberto on parachain XYZ, and if I hash that, it's not exactly like that, but if I hash that information, I'm going to calculate this new account, okay? And so it is non-reversible, and there is no way that someone can impersonate another person, because if it's not me signing, if it's him, the hash will result in something else. And so now this new account is going to be the one that is going to be the message sender now, but it has no signature, okay? So the signature, the VRS value are like 0x1, 0x1, 0x1. And this actually creates a funny situation because if you don't have a signature, you can have transaction hash collusion, because a transaction hash is basically the hash of the signed transaction, all right? And the uniqueness of that is the nonce and the actual signature. And so that's why remote EVM calls have a global nonce, meaning that you can only do Maybe it's a UN256, so there's a limit on the amount of remote EVM calls you can do, but I don't think we'll reach it in a very long time. And so basically now we skip the validation because the validation happens in the Ethereum XCM module, and then everything else is the same. Now you're calling the EVM, and then you're going to execute the call. You're going to get a new state, and then you're going to get some Ethereum logs. I didn't show it because of space, but fun thing is that when you get the receipt here, you will see that the transaction signature is 0x1, 0x1, so it's really dumb. You cannot do easy recover, for example. And that the execution, it's free. Because you pay the EVM execution at an XCM level when you're executing the XCM. You're not paying it at an EVM level. So when we access the EVM here, basically the gas price is 0, and so you're not paying, the EVM is not charging you for the execution because you were already charged beforehand, okay? It's kind of like the two main differences, I would say. And so with this premise, I think I have a lot of time still, but with this premise, the main idea is that Moonbeam can access as a port of call in and out of the Polkadot ecosystem, right? So you have blockchains, like I was saying before, the future is multi-chain, is cross-chain. And so how do we communicate? I mean, how would you do cross-chain integrations that are seamless and super, super nice? I mean, it's a developer's job to do that. It's not easy. But if someone in the ecosystem of Polkadot wants to access assets and services on Avalanche, on Cosmos, on Ethereum, on BSC, they can do it through Moonbeam because we offer seamless Ethereum compatibility. We're connected with all the major bridging providers, GMP providers that exist, and we'll be supporting many more. And so you can create these cross-chain experiences that are simple for users, like I was shown with the example of Prime Protocol. But not only that, you can actually, for example, move liquidity in from Ethereum to a parachain in Polkadot if they need liquidity. I'm going to give you two really cool examples of things that happened on Moonbeam like this. One of them is that I don't know if you're familiar with Osmosis. It's a Cosmos SDK-based chain. They're like a DEX. Let's summarize it like that. And they wanted to get DOT liquidity, right? So you're like, okay, DOT liquidity, so liquidity from Polkadot on a Cosmos-based chain. How would you do it? Polkadot is not connected with any bridge. Like, they don't have any bridging provider, right? So how do you do it? So basically, the way that the guys worked it out with Axelar, us, and the folks from Polkadot is that you go to a UI, you put one dot from Polkadot to Osmosis, you click, and that's it. It works, right? And the way that this works is that via XCM, you're sending dot to Moonbeam, okay? And now you have it in Moonbeam, you have it as an ERC20, this dot. And so now Axelar can say, okay, I'm going to grab this ERC20, and I'm going to move it with Axelar to the Cosmos ecosystem. And then once I have it in my Cosmos chain in Axelar, I'm going to use IBC to move this dots and route it to Osmosis. So you're talking about 3 different GMP protocols working together to create a cross-chain experience, right? It's not 1, it's not 2, it's 3. But ideally, from the user, they have no clue that happened. I mean, they're just saying, I want 1 dot on Osmosis, right? So that is the main idea of connected contracts, that you want to simplify the user experience for cross-chain integrations or interactions, abstracting all the complexities out of end users, because end users should not suffer or shouldn't have to go through the burden of like switching chains and moving around and so on. Yeah, I think that was the main example that I wanted to give. The other example that we're working on right now, it's not actually live, but we're in testnet, is that a lot of these Polkadot parachains, they need liquidity. And so, for example, we have DEXs, parachains that are DEXs, but they don't have an EVM, or they're not connected with any bridges, right? But they need liquidity to work. I mean, that's the whole point of a DEX, right? And so the way that this is working now is that we're providing one-click solutions via Wormhole, in which any Wormhole-connected chain will have a nice-looking UI that you say, I want to, for example, move 1 ETH from Ethereum to this parachain. And what's going to happen is that Wormhole is going to bring that Ethereum to Moonbeam as an ERC20. And then on Moonbeam, this ERC20 can be moved with XCM to the destination parachain, like, for example, Hydra DX. And then they will have liquidity in Hydra DX. And once again, this can be done with 1 click on the user signing a message on Ethereum. It's not multi-hopping, it's not doing anything. And there you have 2 different GMP protocols working together. You have Wormhole GMP to Moonbeam, and then XCM routing that liquidity to the parachain. And we call it Moonbeam routed liquidity. That's like the fancy name. And so I think that's all I had. If you really like the slides, I saw some folks taking a lot of pictures. You can actually just scan the QR code and you'll get access to all the images. I mean, I think we have time for questions, so I'm really open to the discussion, right? I don't consider myself a cross-chain expert. I want to hear like your thoughts on like cross-chain, if you think this is the future or not. Here you have all the things about Moonbeam, Twitter handle, Telegram, Discord, and the website. And then on the right-hand side, you have my Twitter. I'm not I don't do a lot of Twitter, but anyways. And then Telegram, if you want to contact me, if you have any questions and things that you want to learn. If you want to learn more about Moonbeam, I'm always happy to chat. So yeah, thanks a lot for your attention. Is there any questions, any comments, any sort of discussions that you want to get going? Yeah. Yeah. You need to talk to the mic because of the live stream, sorry. So.
Thank you very much for the presentations. So as you mentioned, so you will have different consensus if you are taking liquidity from maybe that ZK rollup or Optimism rollup. How do you manage finality with this workflow?
That is a great question. Let me take a sip of water and I'll get to it. So yeah, rollups are really popular right now, right? They're super popular. Like everyone is talking about Arbitrum, Optimism, and so on. And one of the issues that they actually have is that they have two types of finalities, right? They have soft finality and hard finality. Maybe there are other names. And the feedback that we've gotten from bridges is that they kind of hate L2s because finality can take up to 3 minutes, right? And so it provides a really bad user experience, and also for developers, right? Because for example, in the Prime Protocol example that I was giving, imagine you lock your collateral on Optimism, and you need to wait 3 minutes to ensure that that transaction was final there, so that you can actually pass the message, right? So a lot of the GMP protocols that I showed, they check for finality. They don't check for the transaction inclusion, because they cannot actually do that. They need to ensure that at least a transaction is marked as final on the origin chain, so they can actually execute it on the destination chain. Because they're taking on all the risk. Like if for example, let's say I move 100 million USDCs, I don't have that money. This is just an example. So let's say I move 100 million USDCs from Ethereum to Moonbeam, and that transaction is not finalized on Ethereum, but Wormhole mints this 100 million USDCs on Moonbeam, and then that transaction never happens, it gets reverted or whatever, or reorged on Ethereum. Wormhole is the protocol that is affected, right? Because they cannot pay out for those 100 million USDCs now. So remember that bridging tokens is specifically, it's like you lock assets in a contract and you get a piece of paper that represents that you have these assets on the contract. So if you printed more pieces of paper that you can actually redeem, it's like inflation in countries, right? I mean, they're going to lose value basically, and so. It's going to happen. Like L2s are here to stay, but we'll have other blockchains as well, and there will be caveats in cross-chain communication. For example, developers love interacting between Avalanche and Moonbeam because finalities are so small that the user experience and even testing is so much nicer, right? And so, but I guess they'll have to adapt. That's why also like optimistic bridges are actually a good solution, because you can have intermediate parties that are willing to take on the risk of saying, go for it, buddy. I mean, mint your NFT, your wrapped token on Moonbeam, and I fully take on the risk if this doesn't happen, right? And so I think optimistic bridges will be a solution for like finality lags on L2s, to be honest. But that's a great question. So. Cool. Any other questions, comments? Yeah, so I mean, another thing that I was sort of like discussing like a couple of weeks ago was about L2s as well. That a lot of people think that L2s are going to be the thing, and so they're working on bridging solutions on L2, and that's it. They don't really want to communicate outside of L2, and that provides a really good bridging experience, right? Because if you provide an optimistic bridge on L2, you can just say go for it. The finality is instant, and then you can actually settle on Ethereum L1, and so. I think that their solution is sort of like they don't want to deal with this like finality outside and then this like really bad user experience, and they're just focusing on L2s. And they think that there will be like hubs of L2s secured by different L1s. But yeah, I personally, I don't see that. So cool. All right. Thanks a lot. And yeah, I'll be around if you want to have some questions afterwards. So thanks.